And we're back now with the second part of our 4.3 notes, which quite honestly really belong in section 4.4. So I'm not sure where I'm going to post this just yet. I'm just calling it the 4.3 continued notes. But honestly, guys, you probably don't need to look at this video until you're ready to do the 4.4 homework, because now we transition into the big topic we're going to be doing here in the middle of chapter 4, which is talking about how to graph more complex functions that kind of go beyond the realm of the types of functions you guys have learned to graph over the last several years. So we're going to start talking about how to graph things that defy easy classification into any of the families that you've been doing over the last couple of years. Things that are more complicated than simply quadratic or cubic functions. Things that are like a weird combination of different kinds of functions that heretofore you would not have been able to do. So the first thing we're going to start talking about now is the behavior of a graph. And these are three factual statements, everybody, that we want to make sure that we understand. But I'll leave it up to you as to whether or not you think you need to write them down, because a lot of this is information that we had actually already talked about back when we were doing graph matching at the very beginning of chapter 3. So, three things to make sure that we understand, everybody. If the first derivative of your function is greater than 0, which is a mathematician's way of saying positive, on an interval here from a to b, then we can conclude that the function itself increases on that interval here. So what we're doing here, guys, is we're trying to draw a connection between the sign of your derivative and the behavior of your function. The sign of the derivative tells you something about the behavior of the function and vice versa. But in this way, we just kind of do it in that direction. So any interval on which your first derivative is positive, then we know our function is increasing. Now, the next statement is just the inverse of that. If your function's derivative, f prime of x, is negative on an interval from a to b, then we can say that your function, f of x, decreases on that interval. So put those first two statements together, guys. A positive first derivative tells you that your behavior is increasing, and a negative first derivative tells you that your behavior is decreasing. The kind of unwritten third part right there would be the one that's neither of those cases. If your first derivative is neither positive nor negative, it would have to be 0, and that would mean that your function is neither increasing nor decreasing, and that would mean that it would have to stay constant. But that doesn't happen very long, everybody, so we're not really going to dwell on that. It'd have to be a weird piecewise function for that to actually occur. The third statement right here, to be honest with you guys, is really not very important in the grand scheme of things, but this is where your author introduces the definition of a word monotonic. Okay, and in speech, everybody, the word we would use is monotonous, monotone. When everybody talks in the same tone of voice for the whole time and they don't have any inflection, that is a monotone speaking voice. Well, in math, we adjust that word a little bit and we make it monotonic. And we say that if f of x is strictly increasing, or, that's important now, or strictly decreasing on an interval from a to b, then we say that f of x is monotonic on that interval. That just means that instead of having a bunch of changes in behavior that might occur at an extreme value like a max or a min, with a monotonic function, we'd be talking about one that's strictly increasing or just strictly decreasing. And it doesn't have to be increasing at a constant rate. It could be a function like this that's increasing at an increasing rate. All three of these graphs I've drawn here are monotonic, as opposed to a curve that looks like this, which is not monotonic, because this curve is increasing at first and then it ends up decreasing. So that one has a behavioral change that the three at the bottom that I drew do not. So that's good information to have, but it might be something that you guys know already, and if not, it might have been something that you deduced pretty quickly on your own. So let's dive into a few examples here, guys. You're going to see some homework questions here, and as I said, I believe this is not going to show up until your 4.4 homework. So we're going to state the intervals on which each function is increasing, decreasing, and or monotonic, although we really don't do monotonic all that much. So let's take a look at f of x equals equals negative 1/2 x plus 3. And I know that you know, and you know that I know, that all of us know what this function looks like without even graphing it, and we really could answer this question without doing a lick of work. But where would the fun be in that? Furthermore, where would that help us when the functions got more complicated, like this one or this one? So we're going to try to do all of these the exact same way. The way we get information about the behavior of a function, increasing, decreasing, or monotonic, we get that information from our first derivative. So that's what we're going to have to find here before we do anything else. F prime of x is equal to, and since it's a linear function, its derivative is just its coefficient. So the derivative of this function is negative 1/2. Now the keen among you will notice this derivative is unusual because it is constant, meaning it contains no variables. So what we now would want to do in most problems is ask ourselves, what values of x will make this derivative positive, what values of x will make this derivative negative, and what values would make it equal to 0? Well, as I think you can see, this derivative being constant is negative, which means it's going to be less than 0, obviously, for all real numbers. There is no value of x that's going to make this derivative ever be 0 or ever be positive. So since your derivative is always negative, let's go back to this little checklist. We're now looking at the second case right here. If the derivative f prime of x is negative on an interval from a to b, then f of x decreases on that interval from a to b. So we could say now, because our derivative is always negative, that f of x decreases, because our derivative is negative, really on the interval that starts at negative infinity and goes to positive infinity. Okay, kind of a silly way to answer that question really, because this one was for all real numbers, but that would really be our answer to this. Okay, and in terms then of the second part of that, basically when a function is always increasing or always decreasing, we would say that this one is monotonic on that same interval right there, because it's always decreasing. So I'm not even going to write that one down. Monotonic is not something I'm going to ask you guys on a quiz or a test, but if it shows up on homework, there's a quick little discussion of it. And I don't think a graph here is necessary, but it certainly doesn't hurt. Real quick, let's see, like I said, you guys probably did this in your heads a while ago. You've got a y-intercept of 3 and a slope of negative 1/2, which might look something like that. And sure enough, guys, it looks like that function is decreasing everywhere on the interval from negative infinity to positive infinity. Okay, boring example. Let's do the next one here. G of x now is negative 5 times the quantity of x minus 3 squared plus 4. Now again, the keen of you might already know what's going on, but just in case we're not that swift, or we like to be a little bit more thorough, let's do this problem the way we did the last one. We start off by taking our derivative, g prime of x. We have a parabola here, it looks like, everybody, that's written in vertex form, so we can apply the chain rule here. That 2 for the exponent gets multiplied by the negative 5 to make a negative 10. The base of the exponent, x minus 3, does not change. We lower the exponent by 1. We multiply by the derivative within, which is 1. And while I'm being thorough here, plus the derivative of the constant 4, which is 0. So boy, it sure looks like that is going to be a negative 10 times an x minus 3. Now, could I distribute that negative 10? Absolutely. Should I? No. Factored expressions, everybody, are always what you want. Now, what we are now interested in is knowing what values of x are going to make this derivative positive and what values of x are going to make it negative. To figure that out, we have to consider the spot where positivity and negativity change. And that occurs at the spot where your derivative is actually equal to 0. So now, everybody, we have a factored expression, negative 10 times x minus 3, that is set equal to 0. And this beautiful thing that we use so much that we forget the name of it and we don't really remember exactly what it says, even though we know how to do it, is called the zero product property. It says that a factored expression, A times B, will equal 0 if either A, which is negative 10, equals 0, or that will happen if B, x minus 3, equals 0. And we need to solve each one of these equations. Well, pretty clearly, there is no value of x that will make negative 10 ever equal 0. So forget about that. But now on the second part, we just add the 3 on the other side, and we get x is equal to 3. Now, this is really the first time we're going to talk about this, so this is a pretty significant moment. I will mark it by drawing a star up in the corner, so when you see that, you know you need to stop fast forwarding and actually pay close attention. What we're going to talk about next, everybody, is called a sign chart for the first derivative. Now, the x equals 3 is the only value we came up with where our derivative was equal to 0. And what that means, everybody, is that we just found our lone critical point right here at x equals 3. And a critical point is very often an extreme value, a maximum or a minimum, but not always. And what I'm going to show you now is a way that we can test for that. I put a box around that critical value. And what we have here, guys, is one critical point, x equals 3, and that one value creates two intervals, everything that comes before 3 and everything that comes after 3. So what I'm going to do is draw one line right down here and then kind of make a little T-chart out of this. Okay, where do we go from there, guys? Let's go ahead and let's do this in more of the concrete way. Right here, we are going to pick one value, and there are several that are one value that is less than 3. So probably the easiest number to pick there would be 0, but who cares? Pick 1, 2, 2.7, it doesn't matter. To the right of that, we're going to pick one x value that's greater than 3. So I'm going to go with 4. It makes 0 difference which number you choose, just as long as one is to less than your critical value and one is greater than your critical value. And now that we have those, we are interested in the behavior of this function. Where is it increasing? Where is it decreasing? And to know information about behavior, we do not look at the original function itself. We look down here, you guys, at the value of its derivative. So we are going to evaluate g prime at 0, and then we're going to evaluate g prime at 4, and let's see what we see. Now, this is why I had said a while ago, guys, that the factored expression for g of x is really better than an expanded version like negative 10x plus 30, because all I care about right here is not really the value of g prime of 0, I just care about the sign. So when we put in a 0 for x, the negative 10 is obviously negative, and 0 minus 3 is going to be negative as well. And a negative number times another negative factor is going to give us a positive derivative. And where g prime is positive, let's go back to what we wrote here, and now let's look at the first line. When your derivative is positive, then your function is increasing on that interval. So now that we know g prime is positive, that tells us, and I'm kind of running out of room here, guys, I didn't leave myself a lot of space here, we now know that g of x increases. So I'm going to draw that upward arrow. How's that for formal right there? G of x increases for all x values that are less than 3. Now, we would not want to make assumptions at this level, everybody, so let's test it over here on the right now. When we let x be something bigger than 3, like 4, let's do that same work right over here. Negative 10 is obviously still going to be negative, but 4 minus 3 is now positive. So a negative times a positive gives us a negative product. So for any x value greater than 3, your derivative has now become negative. And anywhere your derivative is negative, that tells you that the original function, g of x, has to decrease. So we now have enough information. I'm going to go ahead and get rid of this, guys. We now have enough information to answer this question here. The directions said state the intervals on which your function is increasing or decreasing. So we can say here, guys, that g, let me do this from left to right, g increases on an interval that starts at negative infinity and it ends when x gets to 3. So g is an increasing function, that was really poorly drawn, on the interval from negative infinity to 3. And then we can say that g now becomes decreasing on an interval that starts at this critical value 3 and never ends, so we'll put a positive infinity right there. And that in the green box, everybody, is the answer to this question. Now, 10 minutes ago, you might have figured this out on your own. I gave you guys a parabola that was already in vertex form, which I know a lot of you guys don't like, and you never learned it as well as you should have, but boy, is your life easier if you do get the hang of it. You guys should be able to tell me that the vertex of this parabola, the way that it was written right here, the vertex is positive 3, positive 4. So your vertex is right about here at 3, 4. You also should be able to tell me that this is a downward opening parabola because a is negative. The fact that your a value is negative 5 means that it's a really skinny downward opening parabola, but that's really not relevant here at all. We've got a skinny downward opening parabola that looks something like this. Now my question for you guys is, does that graph that I just drew gel with this information right here? That the function is increasing on the interval starting at negative infinity and it increases until you get to an x value of 3? Yeah, that's what it does. And then it decreases on an interval starting at 3 and going on towards infinity off to the right. Yeah, that's what's happening here as well. So this is another problem where honestly we maybe didn't need that first derivative test, but it certainly doesn't hurt. We need practice getting used to this idea of a sign chart. Okay, and this last one is interesting, guys, not because the answer is difficult to figure out. I know you guys know what this graph looks like, but a really interesting concept is going to pop up here that I do want to talk about. It's really important. So we're going to find our derivative here. H prime of x is going to be a 3x squared. We're going to set that equal to 0. And you're going to realize very quickly that you divide both sides by 3, then take the square root. You only end up with this one critical value of x equals 0. That is the one and only value that will make your derivative equal 0. And I do want to be clear, x equals 0 is a critical point. Why? Because if you go back to your definition of a critical point from our 4.2 notes, a critical point is any value of x for which the derivative is equal to 0, regardless of whether or not that point is a maximum or a minimum. So just like you saw me do on the last problem here, I'm going to go ahead and make a t-chart here, and we're going to pick a test value less than 0 and a test value greater than 0. No need to think too hard about this, guys. Any number will work. So I'm going to go with -1, and then I'm going to go with x equals +1. And again, we're interested in the behavior of this function, and the behavior information comes from the sign of the first derivative. So we're going to evaluate h prime of -1 and then h prime of +1. Okay, so put a -1 into h prime right here. Make sure you follow your order of operations. -1 squared is 1 times 3 is 3. The value doesn't matter, but the sign does. So h prime of -1 is positive, which means that h increases on this interval from negative infinity to 0. This is why I have you guys box up the x equals 0. That's the value that's actually going to go in your answer, not this value right here, which was random and that we just made up. Now, I said a moment ago, and maybe you caught me here, when I got here and did that, I said, now you would never want to assume that just because your function is increasing here, that it would have to be decreasing here, although that's certainly what happened in this problem. But let's check this one out. When we now put a 1 in for h prime, 3 times 1 squared, that is still a positive number. And that means that h does not suddenly change to decreasing. H is still increasing when x is greater than 0. So the interesting dilemma right here about this problem is this. Do we have two different intervals on which this function is increasing? And the answer to that is no. What's going on here at x equals 0 is that it is, I'll say it again, it is a critical point. Why? Because the first derivative equals 0 at x equals 0. But if you take a look, we do not have a change in behavior because we do not have a sign change in the derivative. And that means that while x equals 0 is a critical point, it is not an extreme value. Now, graphically, I think you guys know what's happening, but let's sketch it out just to make sure here. And this is actually maybe the first time in your life you really need to pay attention to what this graph actually looks like. A lot of people want to draw x cubed looking something like this, and I want you guys to pay very close attention to the fact that I just drew that coming through the origin at about a 45-degree angle. And if I draw it looking like this and like this, you guys might think that that's a pretty good representation of the graph of x cubed. And you know what? Your Algebra 2 teacher and your pre-calculus teacher might have let that slide. But there's a difference here, everybody. The reason this graph is wrong is because if I were to now think about the tangent line to this curve right here at the origin, if I did draw it going through the origin at a 45-degree angle, my tangent line would look like this with a slope of 1. But what do we know? Our derivative is right here. And when you evaluate h prime of 0, the slope of that tangent should actually be 0, which means it should be horizontal, not diagonal. And so for that reason, let me go back a couple steps, the way that I drew this graph is wrong. This is actually almost exactly what happens with the graph of y equals tangent of x. It goes through the origin at a slope of 1. But the graph of y equals x cubed has to be horizontal. This is weird for people to get the hang of. It actually has to be horizontal as it's passing through the origin. So it's not going to do this for very long. But basically, guys, we should draw it looking something more like this. Okay, and now hopefully you can see the difference. Now that tangent line, I'm hoping, actually looks horizontal as it passes through the origin. Now, let's talk about behavior, which was the whole point of what's going on. As we begin this graph, from negative infinity all the way on up here to 0, the function is increasing, and that's what we saw. At 0, it levels out, but only for an instant, only at the value x equals 0. And then, as you move any further again to the right, this function begins to increase again and does that out towards infinity. Okay, and so what that means is that this function is increasing, and here we're going to go ahead and write the answer now, that h of x, and I know last time I just wrote g, you can write g or g of x, it makes no difference. So h of x increases on the interval here from negative infinity all the way to infinity. Now, a lot of people want to break this up and say that it increases on the interval from negative infinity to 0 or the interval from 0 to infinity, but I'm telling you guys that, and it has to do with the parentheses versus the brackets right here, that for that reason, we say that this function increases on the entire interval from negative infinity to infinity. The real reason for that, I don't want to bore you too much with this, is you can choose any 2 points on this curve. I'm going to draw them far away just to illustrate a point. So there's one, and here's a second. And no matter where you draw these 2 points, the point on the right is always going to be higher than the point on the left. That's pretty obvious where I drew them right now. It's maybe less obvious if I draw them really close together, like this one and this one, although it's still true. The point on the right is higher than the point on the left. And then, boy, it's really hard to see, but if I drew them really close together like this, it would still be true. the point on the right would still be higher than the point on the left. And that is why we say that this function is always increasing. We don't have to kind of break it off at 0. Okay, let's move on to 2 new tests right now, and then we're going to kind of see them put together. All right, this first derivative test for critical points is really what I was talking about in the last few examples. So here we go. Let x equals c be a critical point of your function. That could be a spot where your derivative is undefined, or more likely, where your derivative is 0. Then, here we go. If the derivative f prime, dang it, if the derivative f prime, there we go, f prime of x changes from positive to negative at x equals c, then f of x has a maximum value at x equals c. Think about what that means, guys. If your derivative was positive, that would mean that your function was increasing. And then if your derivative becomes negative, that now means that your function is decreasing. So your function was increasing with a positive derivative and then starts decreasing with a negative derivative. And if that happens, guess what? That point right there is a maximum. Inverse of that, if your derivative, f prime, changes sign from negative to positive at x equals c, then you can say f of x has a minimum at x equals c. Let's think about that. A negative derivative means that your function was decreasing. Then it changes to a positive derivative where the function was increasing. And a function that was decreasing and then starts increasing looks like that, and sure enough, that is a minimum. So that's the first derivative test for critical points. And this, you guys, is a pretty important one to make sure that we have down. Gotta be honest with you, the second derivative test for critical points, far less important. So, if you're really pressed for time, you could probably skip this slide, but it's not going to take us very long. Again, it starts off the same way. Let x equals c be a critical point of your function, a spot where your derivative is either going to be 0 or undefined. Okay, then here's what happens. If f prime of c is 0, like we just said, if your first derivative is 0 and your second derivative is negative, then we can say that f of x has a maximum at x equals c. If you guys go back and think about the significance of this statement, which we haven't done a whole lot with, guys, but we did talk about the idea that the second derivative of a function tells you something about concavity. Okay? And if that happens, that means that we're dealing with a critical point where the derivative is 0, and this statement right here tells you that the function is concave downward. Well, if it's concave down, it's got to be cupped that way, and I think you guys can see my point. That has to be a maximum. Other way around now, if you're dealing with another critical point here, and your second derivative is positive, that means that you would be concave upward at that point like this, and guess what? That's the definition of a minimum. The third case, and I indented this one right here, if f prime of c is 0, once again, and your second derivative is also equal to 0, this would be the third possibility, then we can say that f of x has neither a max nor a min at x equals c. And that's kind of what happened a moment ago on the function y equals x cubed, the one we just dealt with. Y prime here would equal 3x squared, and that equals 0 when x is equal to 0. Y double prime, though, would be a 6x. And when you plug a 0 in here, you get your second derivative to equal 0 once more. So that's what happens in a case like this, everybody, where your first derivative is 0, but your second derivative is 0 as well. And as you can see, since this function goes down to the left of this point, but up as you go to the right, this one is neither a max nor a min. In all likelihood, that's a point of inflection, but that's not even guaranteed either. Okay, one big example, guys, and then I think that one was blank. Okay, we're done here after this one. So this is kind of in line with the type of problems that you're going to start seeing in 4.4 and 4.6. Find and classify, meaning are they maxes or mins or neither? Okay, find and classify all critical points of g of x equals this quartic function. So critical points come from your derivative. So g prime of x here is going to equal a 4x cubed minus a 12x squared and a plus 16. Right? Right, that's what we've got right there. And to find a critical point, we would set this thing equal to 0, or, let me do this first, think about what value of x would make this undefined. Well, I hope that you're sick of hearing me say this already, but if a function is a polynomial, its derivative is a polynomial, and polynomials, which we deal with more than any other kind of function, are never undefined. So we don't have to worry about g of x being undefined. We do have to worry, though, about this derivative equaling 0. And in fact, since it's cubic, I know that it goes down on the left and up on the right. It's got to equal 0 for at least one value of x. Now, the good news that I have for you all is that solving cubic polynomials by hand is not something that we do much, if at all, of. So I'm going to go to my Inspire app, guys, just like I would expect you guys to do, and we're going to go ahead and use that to solve this equation right here. So where am I here, everybody? Let me think about how to do this here. I'm going to go to Tools. You guys would hit Menu, and I'll go to Algebra and number 1, and we're going to solve this equation here, which was, if I recall, a 4x to the third power, and that's as much as I can remember. Let's see here, a minus 12x squared and a plus 16. Okay, where was I? Get out of there, and a minus 12x squared and a plus 16. We wanted to know, where is that going to, where did my equals sign go? There it is, equals 0, comma, and we want to solve that for x. Let me double check, make sure I've got that right. 4x cubed minus 12x squared plus 16 is equal to 0, and solve it for x. Okay, and if I hit enter, oh, that's convenient, I got integer solutions. Now, this maybe should surprise you just a little bit. That was a cubic polynomial equation, everybody. We should expect a maximum of 3 solutions from that. The fact that we only got 2 is telling, but I don't want to tell you what that tells us just yet. All right, x equals -1, x equals +2. Those are the zeros that we just came up with. So x equals -1, or, dang it, dang it, dang it, dang it. Get rid of there, get rid of there. All right, x equals -1, or x equals 2. Make sure I got that right there, right? -1 or +2. Okay, now those, everybody, are critical points. Those are values for which your derivative was equal to 0. Okay, so that is good, good, good. But we need to classify those using one of the 2 tests that we just talked about. And I told you guys that we are almost always going to use the first derivative test and hardly ever the second. So we're going to make now a more complicated chart than we made before, because for the first time we have 2 critical points. And 2 critical points split your x-axis up into 3 intervals. First, we need an x value less than -1. So how about -2? Then we need an x value in between -1 and 2. So how about x equals 0? And lastly, an x value greater than 2. So how about x equals 3? And since we're interested in behavior now, we're going to plug these test values into the derivative. So we're going to evaluate g prime of -2. We're going to do g prime of 0 and g prime of 3. And unfortunately, you guys, since I didn't factor this thing by hand, I actually have to go to the messy expanded expression here and plug these numbers in. But I feel like I can do this without a calculator. All right, let's plug in the -2. -2 cubed is -8. -8 times 4 is a -32. -2 squared is 4. times 12 is 48. So we're at a negative 32 minus 48. That takes us down to a negative 80. Negative 80 plus 16 is a negative 64. Remember, I don't really care about the value. I only care about the sign. But that number is going to end up being negative, less than 0, which tells us that g is decreasing on that interval. Okay, what's happening next? You would probably assume that since on the first interval g was decreasing, that on the next interval, the one right here, g would be increasing. But let's not assume. Let's plug a 0 into that derivative. So plugging a 0 in here, well, pretty easy, guys. 0 minus 0 plus 16, our derivative is now positive. And that tells us, as we assumed, that g is increasing on this interval. And then you'd probably assume that because your function was decreasing, then increasing, that it's probably going to end up decreasing again. But let's not assume. Let's plug a 3 in there and see what happens. Boy, I got a lot of mess going on with underlines here, so let's see if we can't clear that out and maybe start over now. Okay, here we go. Plugging in a 3. 3 cubed is 27. Whew, 27 times 4, 54 doubled is a 108. Gotcha. Minus 12 times 3 squared. Well, 3 squared is 9. 9 times 12 is 108. So 108 minus 108, as dumb luck would have it, is 0. And 0 plus 16 is 16. So our first derivative now on this rightmost interval is again positive, which means again that g increases on that particular interval there. And if you guys look at these 3 statements down here on the bottom, the function decreases, then increases, it kind of gels with what I was talking about right over here. No, I take that back. I lied. It doesn't gel at all with that information right there. It gels with what we might have known, or might have thought about if we had discussed it, about what we know about the original function right here of g of x. All that really matters in determining the behavior here is that g of x is a positive 4th degree function. That means that it goes up on the left, and it also goes up on the right. And if we read that now, you guys, from left to right, we start off decreasing and we end up increasing. Let me say that again. We start off decreasing and we end up increasing. Now, that doesn't give you the full story of what happens in the middle, but that's kind of what we know right here. So the directions for this problem were to find and classify all critical points of g of x. We've come up with the 2 critical points here and here, but now let's work on classifying them. What happens at x equals negative 1? Our first derivative was negative. Now it turns positive. Now that means that our behavior was decreasing and is now increasing. And a spot where your derivative changes from negative to positive, or where your behavior changes from decreasing to increasing, is the definition of a minimum, everybody. So I'm going to go ahead and answer this right here, and we're going to say that g of x has a minimum. It didn't say what kind right there, and we don't have to give it to them that way. Has a minimum at x equals negative 1. And the reason is important, guys, because its derivative, g, that's what I meant, not f, g prime of x changes. And we got to be specific now, from negative to positive at that value, x equals negative 1. That, everybody, is a really thorough and proper explanation for what's going on right here. At negative 1, we had a minimum because our derivative was negative and it changed to positive. And that's exactly what we said here. The second critical point, everybody, let's go back, was right here at x equals 2. And what happened there? Our derivative was positive, and then it was still positive. We don't have a maximum or a minimum at that second critical point. Okay, so now we would say for the second part of the answer right here that g of x has neither a max nor, is really the word here, guys, nor a minimum at x equals 2. And the reason for that would be because g prime of x does not change sign at x equals 2. And that's as specific as we need to be here, guys. Does not change sign at x equals 2. Okay, so we've identified the two critical points, x equals -1 and at x equals 2, and we've talked about how the first one, at x equals -1, was a minimum, and we explained why. And then we talked about how the second one was neither a max nor a min because the derivative does not change sign. Okay, I want you guys to notice I did not use the naughty word in writing down either of my answers here, and that naughty word is it. You don't want to use the word it when you're explaining the relationship here with two different functions. Because when people are talking about it, it's not clear whether they mean g of x or g prime of x. So every time I went to name a function, I used its proper name. G of x, g prime of x. G of x, g prime of x. Don't use the word it, everybody. Okay? That it is going to get you in trouble, and it lends an air of ambiguity to your explanations that your AP graders are not going to enjoy. Okay, that's a good spot to quit, I think, because I have nothing else written here. And I think when this info ties in with what we're going to do in our notes in 4.4 and 4.6, it's going to move us towards that larger goal of being able to graph some really complicated functions on our own without a calculator. All right, everybody, good luck.